What's up guys, it's Imran Fiaz and today's video is on AQA level chemistry, acids and bases, part 2. I could have done this in one go, but I was just, you know, I could tell my focus wasn't not my focus. I couldn't, my brain power. I was just getting extremely mentally exhausted, so I was just like, okay, I'll eat and I'll come back to this. And I'm gonna even skip this question as well. Part D. It wants me to calculate pH. So in order to calculate pH, I need the concentration H plus ions. Yes. So Ka, it says before K, before the addition of any sodium hydroxide. So therefore, concentration H plus is going to be squared. Over the concentration of whatever we're working with, which is I need the previous answer, which is 0.0960. So over 0.0960. Because remember, before any addition of sodium hydroxide, concentration H plus equals the concentration of A minus. Again, put this on a flashcard, memorize it, whatever you want. Then rearrange it. Ka, I've got Ka, that's Ka. Rearrange it, and then just substitute it into pH. Equals minus log 10. Concentration H plus 2.0. Okay, calculate pH solution when half of the acid has reacted. So when half of the acid has reacted, that means we have now reached something called half neutralization. It's a very small topic, this, a very small subtopic in acids and bases. But again, you could get this as a 1 marker, which you probably will. So at half neutralization, the pH at half neutralization equals pKa. Again, this one, please memorize this because they don't ask too many questions about this, so definitely could come up. So the pH equals a pKa. And what is a pKa? Well, pKa equals minus log 10 of Ka. Again, another expression you have to memorize. So hopefully you're getting the point. Acids and bases, a lot of it is memorization of these expressions, these formulas, these assumptions. The pH at half neutralization equals pKa. Memorization, guys. So then minus log 10 of Ka, which is 2.62 times by 10 to the power minus 5, which will give me 4.58. Plot your answers to part D and E on the grid in the figure above. Part D and part E. I'm not going to do that. Yeah, all you do is so let's have a look. Part D, 2.80, that's the pH. So you go to 2.80, and then that's when before addition of any sodium hydroxide. So that would be here, right? Something like that. And then same thing for the other one. Okay, question 12. So yeah, please guys memorize this. pH at half neutralization equals pKa. 2,4,6-trichlorophenol is a weak monoprotic acid. Alhamdulillah. With Ka, that what is the concentration of hydrogen ions in this much solution of this? So it's a weak acid. with Ka this, what is the concentration in molybdenum mass cube of hydrogen ions in this much? Okay, so the main thing that gives it away is the weak acid. So I'm gonna have Ka equals concentration of H plus squared no over 2.00 times by 10 to the power minus 13, and then surely I just move it to the left hand side and then square root it. Let's have a look if that works. It should work. 2.00 times by 10 to the power minus 3. I just square root my answer. 7.09 times by 10 to the power minus 6. Perfect. Perfect. The main indicator for me, the weak acid part, and then therefore you make the assumption concentration H plus equals concentration A minus. Like with these topics like acids and bases, thermodynamics, rate equations, NMR spectroscopy, transition metals, I think those are the main ones. You can't revise them like the day before the exam. There's just too much. Like you have to be exposed to past paper questions. What I'm trying to say. Question 13 was a pH of this plus hydroxide. So Kw equals concentration H plus times by the concentration OH minus. I want to find the pH or something. So I'm going to write down the expression for pH, which is minus log 10 of H plus, concentration H plus. And then I'm going to rearrange this expression to find out the concentration of H plus ions. If you don't know what's going on, then you really do need to go through the textbook. I'm not saying that's a bad thing, but you just need to review the textbook. That's it. So what is the pH of this, of potassium hydroxide? So it's going to be the Kw over this. And remember, always do this. Draw out the formula. Because this is luckily, fortunately, this is monoprotic. Right? So I don't need to times it by 2 or anything. But if it gives me another one, then I might have to times by 2, I might have to divide by 2. And then that's where students start to lose marks. And these multiple choice questions, you make one mistake, all that working, you've just lost a mark. Savage, but that's how the game works, my friend. 13.66 once you've done all of that, and then substitute that into there. So the answer is B. Question 14. The diagram shows a pH curve produced by, I want to zoom out a bit so I can have a look at the full thing. Strong alkali to weak acid. Okay. Which point in the curve represents a solution that can act as a buffer? Okay. It's obviously going to be B then. Just by looking at it. Well, A, you go to there, but B, it's just like that. C, you're going up. C, you're going to there. And then D, you don't know where that's going to continue or not. So B is the point of the curve which can act as a buffer. Obviously, I don't want to just tell you the answer. I want to explain it to you guys. So in terms of explaining why it's only B and not A, C, and D, well, if you didn't know exactly what you were doing, use process of elimination. let's explain each part because this is really important. Because this is when I see these kind of questions, these kind of multiple choice questions, they can be easily repeated, easily repeated. I mean, they don't reuse questions. They do. They do. They definitely do. Easily, not repeated, reused. So you have to understand what's going on. So with point A, well, this is the pure weak acid. This is when we've added 0 amount of alkali. So it's a pure weak acid, and we know it's a weak acid because it tells us in the question. Then with B, this is before the steep rise, this steep rise, and this is called it's called the buffer region, and then therefore it is buffer. C, that's near the equivalence point, so it can't be C. D is after equivalence. So with after equivalence, then I've just got after equivalence. I just got a lot of excess strong alkali, and that's not what I want. I want a solution that can act as a buffer, so we can resist changes in pH by adding a small amount of acid or alkali. So therefore, the only place it can be is B. Give the meaning of the term Bronsted-Lowry acid. I will do that. It's very, very simple meaning. Proton donor, that's all they want. What is meant by the term strong when describing acid? Completely ionizes to form H plus ions in water. This much of solution with this much contain this much of hydrogen ions, calculate value for pH. Alhamdulillah. So if I want to, I'm just having a look if there's any previous information. It says calculate value for pH. So I'm gonna say, well, it's telling me 298 Kelvin. So immediately, obviously, I'm thinking about it tells me it's a strong acid, so therefore completely dissociates to form H plus ions. Also tells me some monoprotic acid, so only releases one H plus ion. I could do, I guess, but if I do, at 298 Kelvin, 25 cm³ solution of this contained at 298 Kelvin, 25 cm³ solution of a strong monoprotic acid contained 1.45 times by 10 to the power minus 3 moles of hydrogen ions. Calculate a value for pH of the solution. Answer to 2 decimal places. Well, before I carry on, even if it doesn't give you this, always, and please, I mean this, always give your answer to 2 decimal places. Okay, I see where I went wrong. I don't know why I didn't see that. Okay. Okay. No worries. This is the number of moles. This is the volume. I don't care about that though. I want the concentration of hydrogen ions. So the concentration of hydrogen ions, moles of concentration, volume concentration is the moles, which is this number, which I'm going to say y, over 25 centimeters cubed, which I'm going to say x. So it's just going to be 1.45 times by 10 to the power minus 3 over 25 times by 10 to the power minus 3 because I want it in moles per minus cubed. Then I substitute it into the expression pH equals minus log 10 H plus, so minus log 10, 1.24. Okay. Calculate pH solution form after the addition of this much to the original 25 centimeters cubed nitric acid. So pH after you add this much to this much, the original this much. So I've got the moles of sodium hydroxide, which is 5.25 times by 10 to the power minus 3. And I'm adding that to this thing here, to the acid, right? But what I can spot here is I need to now find the moles of hydroxide ions in excess because I've got this addition of this, right? I'm adding this hydroxide ions to these hydrogen ions. I can clearly tell that the hydroxide ions are clearly in excess. So when I'm reacting the hydroxide ions with the H plus ions, I'm basically subtracting them. And it makes complete sense. It does. If I've got two things and they react together, what am I going to be left with? Well, therefore I'm going to subtract them to number of moles, and I get 3.80 times by 10 to the power minus 3. And then it gets a lot easier from there. Then you find out the concentration, because that's the moles, find out the concentration, and that's over the volume, which is times by, yep, and then you just rearrange the KW expression, and then that's it. Honestly, the only difficult part is just identifying the first part. Well, if I'm adding this much, so first look at the moles, then I can clearly tell. So with these questions, you always need to identify which one's in excess. Then once you identify which one excess, okay, so I'm subtracting that because it's reacting with that, and then that's it. And then you get pH as 12.80. I say that's it, but then the rest of it is light work for you guys. Concentration, rearrange the KW expression, find H plus, substitute it into pH equals minus log 10 of H plus. Light work. But the first part is difficult for a lot of students. Then it says a buffer solution is made when this much is added to this much of a weak acid, and it gives me Ka, so I'm going to write Ka, and it tells me for Ha, so that tells me that is, for whenever it tells you something for Ka, that's always the denominator. So I've got Ha on the bottom, the concentration obviously. I've got H plus here at the top, and then A minus at the bottom and the top as well, numerator. This much of hydroxide ions added to this much of weak acid Ha. So I've got the concentration of the weak acid Ha. That's the concentration, which is really nice. But what I need to do is I need to find out the H plus. Well, I know it's a weak acid as well. Yes, I know it's a weak acid as well. So therefore, it's going to be a 1-to-1 ratio. And then you just do your normal stuff. And you get 4.27. Normal stuff, rearrange expression, find H plus, substitute the pH equal minus octane H plus. Actually, no, I can't just say do your normal stuff. I have to go through the step by step. Okay, so first things first, moles of sodium hydroxide, obviously, because it's giving me the mass. Work out the moles. 1.50 over 40, yes. Which we can just leave like that, right? And then I know I'm adding this this solution of weak acid, which I work out the moles of. Well, it's just 1 times by 0.150, so that is 0.150 is the moles. And then think about it, okay? 1.50 divided by 40. Now is really, really important stuff. So I've got 0.0375, right? And I'm adding 0.150 of the weak acid. Well, if I'm adding the weak acid, I'm subtracting 0.150. That's exactly what I'm doing because it's going to react with it. So how much moles of the sodium hydroxide is left? That's all it wants me to do. Oh no! I've done it the other way around because that's, you always do it from whichever is in excess. So obviously the acid is in excess. So then I'm minusing the 0.0375. Yeah, because this is in excess, which is the weak acid, and it's reacting with these hydroxide ions. And then I want to work out how much, anytime I want to work out how much excess, how much moles of excess is left. And that's why you always do the excess minus whatever you're working with. Then you work out the moles of that, 0.1125. And then you rearrange the K expression, substitute values in, and then you get pH 4.27. So yeah, you can skip that. The rest of the part is relatively easy. It's the, okay, that's the concentration. Okay, now I need to work out the moles, sodium hydroxide. Okay, I'm reacting with the HA. Which one's in excess, first of all? The number of moles. Well, it's clearly the weak acid. So I'm going to do the excess minus the hydroxide ions, the moles, and then I'll get my new amount of the HA, the moles. Then I'll work out the concentration of HA. And then it's easy from there. Rearrange K expression, substitute it into your pH expression. Okay. Carrying on. Not too many questions left. The graph was obtained from experimental acid reactant alkali. Alhamdulillah. Suggest possible formulae for an acid and alkali that could be used to produce the curve shown in the graph. So I'm gonna go to my textbook because I haven't memorized these curves, which you have to, obviously, because you can't just pull out your textbook during the exam. It doesn't work like that. So I'm comparing this shape, and I can clearly see it is a weak base strong acid. Yeah, weak base strong acid. So for the acid, it just needs to be a strong acid, and for the alkali, it has to be a weak alkali. So strong acid, hydrochloric acid, weak base, ammonia, anything really. Bit of a weird one because it just says suggest a formula, so it could use any, as long as it's strong and as long as the alkali is weak. Practical procedure to obtain data which could be plotted. So with this, it is the pH meter practical pH meter thing. Once you spotted that, then it's just okay. Regurgitate it. So we place a fixed volume of alkali in a flask. Add acid in small portions from a burette. Stir and use a pH meter to record the pH after each addition of acid. Suggest how the practical could be refined to identify most to indicate it. Anytime it asks you suggest how practical could be refined, just think logically. Just repeat the experiment. In this case, with each indicator, select indicator that changes color. If I just said that, I don't think I would have got the mark. Rapidly. Any of them can change color, but it has to be rapidly within when the pH within the vertical part of the curve is when the pH changes from 7 to 4. Yeah, from 7 to 4. Very, very, like these questions, memorize them, man. This one definitely, and this one again. Easily can be repeated. Suggest a suitable piece of apparatus to measure out sodium hydroxide solution. Burette. And the reason you know this is it literally says then explain why this is more suitable than a pipette. So you obviously know it's a burette, but then the reasoning is where most students would probably muck up on. Like, why? It's because it can deliver variable volumes. That easy. Use information from curve explaining about endpoint would be difficult to judge using an indicator. Change in pH is gradual. Yeah. The change in pH is gradual. Indicator would change color over a range of volumes. Well, what are we adding of sodium hydroxide? I don't know why it keeps going there when I'm right here. Oh, sodium. Sodium. pH is that calculate concentration hydroxide ions. So Kw equals obviously H plus OH minus. It gives me the pH, so H plus equals 10 to the power minus pH, which equals 10 to the power minus 11.8. And then I'm going to find the hydroxide ions, so consider hydroxide ions equals Kw over that answer. Which will give you 6.33 times by 10 to the power minus 3. That is a nice 3 marks. Very nice, 3 marks. Okay. And then we move on. The expression for the acid dissociation constant for aqueous ammonium ions. So whenever it asks you to give a K expression, it doesn't in this case, but if it did, for whatever it is, so if it's for, in this case, ammonium ions, well, that is going to always be the denominator. Perfect. The initial concentration of ammonium chloride solution was that. Okay. First things first, check how many marks it is. Always check, because if it was like 6 or 5, then I'm like, okay, what I'm thinking isn't going to be right. Because I was thinking of around about a 2-3 step process, which would get me the answer. But then if it's 6 marks, it's like, okay, it's got to be 4 or 5. So always check the marks. So what's going to happen is that because before any sodium hydroxide has been added, the concentration NH3 equals concentration H plus, because there's no sodium hydroxide added. So therefore Ka now equals the concentration H plus squared over 2.00, which is a concentration NH4 plus ions. And the concentration of H plus is 11.8, 10 to the power minus 11.8. Actually, no, it's not. It says use the pH of this solution. What is the pH of the solution? Oh, before any sodium hydroxide added. So we need to now go back to the titration curve, which is really annoying. Like you have to scroll back a few pages, and in the exam, that's going to be very annoying. 4.2, 4.4, 4.6. So you can see how these questions can get difficult. Like you got to scroll through pages back, check this, then use this. So the pH is 4.6, but that is not even what I want. Then I need to use concentration H plus equals 10 to the power minus 4.6. And then I just substitute it in. I calculated the rest of the work. I get the answer as 3.15 times by 10 to the power minus 10. Like that is definitely a bit more difficult than those 3 marks. Then it says the solution contains equal concentration of ammonia and ammonium ions. So concentration NH3 equals concentration NH4 plus. I just want to write it in this way because then you can like see what's going on. Whereas if you just see that it's not really in terms of chemistry, kind of chemical, you know what I mean. Use the value of Ka to calculate pH of a solution. Okay, so I know concentration of NH3 equals the concentration of NH4 plus. So what was my Ka expression originally, right? It was Ka equals concentration NH4 plus, because that's always on the bottom, the ammonium ions, equals the concentration NH3 bracket concentration H plus. It was that. Obviously, and then we were told in sodium hydroxide added, and we assumed that. But the original Ka expression, without any assumptions, is that, well, what do you notice? If, according to this question, a solution contains equal concentration of ammonia and ammonium ions, well, then these cancel out then. If I've got Ka, let's work with numbers, for example, 10 times by H plus over 10. These 10s will cancel out. And therefore, I'm left with Ka equals, that was just a visual, like using number to show you what's going on. Ka equals concentration H plus. Okay. So if Ka equals a concentration of H plus, minus log 10 of Ka equals minus log 10 of H plus. The reason I take the minus log 10, I will explain that in one moment. Because it asks me for the pH, and pH is minus log 10 of H plus. So that's why I take the minus log 10 on both sides. And then therefore, if minus log 10 Ka equals minus log 10 of H plus, this pH expression, this minus log 10 of concentration H plus, can now be replaced by minus log 10 of Ka. And therefore, what I'm actually working with is pH equals minus log 10 of Ka. And I have got Ka from part D. So it's minus log 10 of 3.15 times by 10 to the power minus 10. And therefore I get 9.50. That is very, very difficult. That is very difficult, this question. Part E. So first part, okay, equal concentrations and they cancel out. Then you get Ka equals concentration H plus. Then you know, okay, if my final result, which is pH equals minus log 10 of H plus, let me take minus log 10 on both sides. So you get minus log 10 of H plus equals minus log 10 of Ka. Then you know the pH expression is minus log 10 of H plus. Right, you know that, which you memorized. And then you're like, okay, with minus log 10 Ka equals minus log 10 H plus, I just replace minus log 10 H plus with minus log 10 Ka. Therefore, pH now becomes minus log 10 of Ka. And I've got Ka from part D, and then substitute into the question. Very difficult. But also very useful. Very, very useful question. Question 18, which statement is correct? I've got pKa's. Remember, Ka equals 10 to the power minus pKa, whereas pKa is minus log 10 of Ka. Yeah, Ka. I think that's correct. Anyway, so which statement is correct? Propanoic acid, stronger acid, butanoic acid, methane. No, I know that's not correct. The value of Ka is greater than this for butanoic acid, for propanoic acid. Well, let's think about it, right? Ka equals 10 to the power minus pK. So if I'm doing 10 to the power minus 4.87, if I'm doing something to the power of something that's greater but is negative, I'm going to get a smaller value. So yeah, that tried to trick you out. So definitely not B, definitely not A. Value of Ka is this. Okay, these ones are relatively easy. You just substitute the calculator using Ka equals 10 to the power minus pK. So I'm just going to do 10 to the power minus 4.7. I get 1.35 times by 10 to the power minus 5. Therefore, the answer is C. And let's check out D. Well, D would be 10 to the power minus 6.5, 6.61 times by 10 to the power. I'm assuming that says to the power minus 4, but it says 104. And you get 0. So yeah, it can't be D. What is the pH of this much of a solution of diprotic acid which is completely dissociated? Okay, big clue. Diprotic acid releases 2 H plus ions. Once you get your head around that, then it is relatively easy. So, what is the pH of this much of a, what is the pH of this much solution of this, which is completely dissociated? So I need to find out, okay, so I know pH equals minus log 10 of H plus, right? And now here's the tricky part. I've got the acid, right? Isn't that the answer, Iman? I just substitute that in. No, it's a diprotic acid. So then I times it by 2, Iman. No. Okay? It tells me this is the solution of a diprotic acid. So that was with 2H plus ions. But in the pH expression, I want 1H plus ion. I want the concentration of 1H plus ion substituted there. So I'm not going to do minus log 10 of 0.020 times by 2. Actually, no, I am going to do that. Because diprotic acid, which is completely dissociated, so releases 2H plus ions. Therefore, I'm going to times it by 2. My bad, guys. So then, yeah, you times it by 2, and then you get 1.40. Question 20. Alhamdulillah. The acid dissociation constant of weak acid has a value this. What is the pH of this much of HA? Alright, so I'm just gonna write down the K expression because I'm gonna be honest with you guys, I don't fully understand what's going on, which is fine. It says the K of this, so that's always the denominator. Because once you start to like draw an expression, write down an expression, or write down some formulae, then you start to see, okay, so then I need to do this and this, because in reality, I'm trying to do some mathematical calculations. I'm working with numbers here. So me just like thinking about it isn't really going to be useful. Writing down some expressions which are relevant, writing down some formulas which are relevant will help me. Okay, so I've got this, which is your average Ka expression, and it says this has the value of this. So let me write that down. Ka equal concentration H plus A minus over HA. No, sorry. The Ka has the value of a weak acid, HA has the value this. So that is the Ka value. It's 2.56 by 10 to the power minus 4. And I want to find the pH of this much of HA. So when I substitute that into there, what do I get as pH? Well, I know it's a weak acid. Alarm bells go off. Concentration H plus equals concentration A minus. And therefore I get Ka equals concentration H plus squared over HA. And then I rewrite that as concentration H plus equals the square root of Ka times by concentration HA. And it gives me both those values, so I just substitute in there. And then I substitute my answer into pH equals minus log 10 of the concentration H plus. Whew, okay, so square root of 4.25 divided by 10 to the power minus 3 times by 2.56 divided by 10 to the power minus 4, and then minus log 10 of my answer 2.98. You know, you might think this is an extremely difficult question, but I have seen harder questions than this, than acids and bases. I'm not saying this isn't a difficult question. It is a pretty difficult multiple choice question, but I have seen harder ones. So you do have to be ready to spend, to go through all these steps in order to attack the multiple choice questions. And that is the end of this question paper. Hopefully you guys find it useful. Um, I will be posting very consistently now until paper one, and then obviously into paper two and paper three. But I just got my psychology exams, paper one and paper two out of the way, and now obviously I'm focusing on the June exams.